So we're going to start talking about galvanic cells. Again, for tomorrow, finish up what you didn't finish on Wednesday because that was kind of a long worksheet, and then you can start on this stuff. So let's talk about galvanic cells. This is 17.2. Our objectives. We're going to describe a galvanic cell and its components, sometimes called voltaic cells. We will use cell notation to symbolize the composition and construction of galvanic cells. What is a galvanic cell? Galvanic cells are composed of two half cells, and each half cell has a redox conjugate pair of a single reactant. A redox conjugate pair is the species you pull for the half reaction when you balance these equations. There is an electrode in each half cell. The electrode is always a solid conductor and connects two wires. Here is a drawing of a galvanic cell. The copper electrode is in copper sulfate solution. Copper solid and copper ion, Cu2+ in this case, are our redox conjugate pair. The sulfate is a spectator, a necessary spectator, which we'll talk about in a little bit, but a spectator nonetheless. Now on the other side, we have zinc solid and zinc ion. This is our redox conjugate pair. And again, we have sulfate as our spectator. There is some special vocabulary for galvanic cells that we need to remember. Oxidation happens at the anode, reduction happens at the cathode. I remember this as an ox is chasing a red cat. Why? The visual of a gigantic oxen chasing a tiny red house cat is easy for me to remember. Anode, oxidation, and reduction, cathode. Hopefully this helps you to remember as well. Anode oxidation, cathode reduction. We also have a salt bridge. The salt bridge will carry an inert electrolyte from one side to the other. In this particular example of a galvanic cell, that is the sulfate ion, SO4 2-. All right, so we'll put that into our salt bridge. I said it was a spectator, but that doesn't mean it doesn't have a purpose. So what's happening here? We have oxidation going on. In this case, it's happening at the zinc electrode. So oxidation anode, which makes the copper electrode the cathode. All right, we got those labels in there. What is happening here? At our anode, we are oxidizing, so we're getting more positive. So in other words, the solid zinc is becoming zinc ions. We're losing some of that electrode. As we lose that electrode and we create some positive ions in solution, we need to balance the charge overall in the solution. It needs to be balanced so we can keep moving electrons. So the sulfate from the copper side moves across the salt bridge and into the anode side. So we're going from cathode over to anode for the inert salt. On the other side, we have positive copper ions becoming copper solid. It makes fuzzy bits on our copper cathode. As this happens, we need to balance the charge. So when we lose the sulfate ion out of solution, it balances the overall charge. Without the salt bridge, a galvanic cell will not work. The charge must balance out or the reaction will stop. We can't make electrons flow if we can't balance the charge. So we must have this particular component. The final component in this diagram is a voltmeter. Normally it will be an external circuit of some kind. Voltage is potential to move electrons. voltage may be positive or negative depending on how you set up the connectors. So when the black is on the cathode and the red is on the anode, you get positive values. Batteries are galvanic cells. We pull charge out of them by using a redox reaction. The external component on a battery might be your phone, your laptop, maybe a novelty light, something like that. Whatever. The external component is where you're putting the electrons. Electrons flow from the cathode to the anode. The current flows in the opposite direction. Okay, and let me correct my mistake here. We'll make that an E minus, because that's what it is. All right, so now we know which way the electrons flow, which way the current flows. When you put the black connector from the voltmeter onto the anode and the red connector onto the cathode, you will get a positive potential. If you switch the two, you get a negative potential. The two values will have the same magnitude. The potential of a cell depends on what we choose to put into our galvanic cell. So the metals that we choose determine how many electrons we can move. This is based on band theory, which you may or may not remember from Chem 107. So when you're talking about molecular orbital theory, that's when it may have come up. By definition, galvanic cells undergo spontaneous redox reactions. Non-spontaneous redox reactions happen in electrolytic cells. Therefore, galvanic cells have a negative delta G value. We'll put that in as an inequality. All right, so now we know the components of a galvanic cell. Let's talk about what chemists do to represent them. You've likely realized by now, chemists like to simplify things as much as possible. There is a way of representing galvanic cells called cell notation. We follow 3 rules for cell notation. 1, half cells are represented by their chemical formulas or chemical symbols. 2, all interfaces between components are represented by vertical parallel lines. The interface between phases is given by a single line, and the salt bridge is given by 2 parallel lines. If 2 or more components are present in the same phase, their formulas are separated by commas. And 3, by convention, cell notation begins with the anode and proceeds left to right, identifying phases and interfaces encountered within the cell. They end with the cathode. We need examples for this. It's a little too abstract right now. Our first example is the galvanic cell that we used to illustrate the parts of a galvanic cell in the previous slide. So in this case, zinc was the anode. There we are, zinc. We start with the zinc electrode, which was the solid. We have a vertical line indicating the phase boundary between solid and aqueous. And then we have our zinc 2 plus aqueous. And we are also giving the molarity. The molarity is important for a lot of types of problems that we will do with this stuff, but it may or may not be included. It depends on what you're doing. So sometimes this component is not there. We ignore the spectator ions because we ignore that in our redox net ionic equation. All right, so after we have our anode part, we have 2 vertical lines to indicate the salt bridge, and then we have our cathode. We give our aqueous phase first, a vertical line indicating the aqueous and solid boundary, and then we have our electrode on the right. And again, we're giving the molarity, but we don't necessarily have to. Our second example is going to be more complicated, but it's going to illustrate some of the other points in our guidelines. So in this case, the electrode material, the anode, is platinum. And the electrode on the other side, the cathode, is also platinum. So our electrodes are platinum, but they are not part of the redox pair. The redox pair on the left-hand side is chlorine gas and chloride ion, both of which are not solids. So if we don't have a solid, then we have to use an electrode of a different type of material. On the right side, we have two aqueous components, which again can't be used as a solid electrode, so we have the platinum for our solid electrode. So let's talk through what we've got here. We've got our electrode. We have our anode conjugate pair, which is the chlorine gas and the chloride ion. We have interfaces between solid and gas and aqueous, so we have vertical lines there. Then we have our salt bridge. And on the other side of our salt bridge, we have both of our aqueous components given by a comma in between. So that's what this was talking about in number 2, the comma. We have another interface given by a vertical line, and that's the one between aqueous and solid phase. And we have represented our entire cell in that way. Now, the electrodes are an important part of this, but they are not actually part of the redox conjugate pairs. Expect to see lots of examples with things like platinum electrodes, possibly gold electrodes. Those are common materials to use to transfer charge from one side to the other. They're nice and conductive and relatively chemically inert. So let's try to go from cell notation to a redox reaction. Let's summarize this information. Galvanic cells contain 2 half cells, a salt bridge connecting those half cells, and an external circuit to put it all together. Half cells have redox conjugate pairs of a single reactant. Anode, oxidation, cathode, reduction. So our electrodes are called the anode and the cathode. Anode, oxidation, reduction, cathode. The salt bridge carries an inert electrolyte from one side to the other to balance charge. External circuits, in most cases a voltmeter for our purposes, but it could also be batteries, charging devices, so your cell phone, your laptop, whatever. Electrons go from the anode to the cathode, and the current flows from cathode to anode. All galvanic cells have a negative delta G because they are, by definition, spontaneous. Cell notation is used to represent galvanic cells. The rules are in the yellow box. And we have examples. Our platinum electrode with chlorine gas and chloride ion, neither of which is a solid. You need the platinum electrode to make the electrons move from one side to the other. And on the other side, we have 2 aqueous components made of iron, which also needs an electrode because you need a solid electrode that is a conductor.